So we've done some math with chemical reactions in our class. The most common thing we've done are chemical reactions that take place in water or in aqueous environments. And so let's look at a couple of these and make sure we can clear them up so that it makes sense when you take the test and organize your thoughts. So the first one we did, we took a container and we had silver nitrate solution in it. And I'll say AQ to stand for aqueous, saying that that is dissolved in water, and we put a piece of copper in there. Okay. And so what happened? Well, the chemical equation for what happened looks like this. Copper metal, I'll put a little solid there to say it's a metal, or I could put a 0 there to say it's a metal, reacted with silver nitrate, AgNO3, and I'll put a little aqueous there, and made some stuff. Okay. So how do we approach these problems if you're given starting information? Well, for example, if I gave you 5 grams of the copper and 300 milliliters of this solution, and let's say it's at 0.5 moles per liter, we've been trying to figure out, well, how do you know which pile runs out first so that you can determine the limiting reactant and therefore the amount of product? Well, how do you do that? Well, first you need an equation that actually describes the reaction. So as soon as you see aqueous in my class, you immediately have to say, well, what's really going on is this container does not have any silver nitrate in it. It has silver ions and nitrate ions. Okay. And there's the piece of copper. And we learned in class that in this particular reaction, it's the silver ions that are reacting with the copper. And so we had an equation. What I'd like you to do, every single time there's an aqueous, and you'll see as we go through this video, every time there's an aqueous, rewrite the equation so that you have the separate ions. Oops, NO3 minus, okay? NO3 minus. Okay, so what we have is copper metal, silver ions, and nitrate ions all in the same container. We learned in class, because the solution slowly became blue, that it was forming copper 2 ions. There was a metal that formed on the copper that we determined was silver metal, and the nitrate ions sort of floated around. Okay, and so we had a name for the ions that didn't do anything. They were the spectator ions. Okay, so what we did next, and that's what I'm requiring, is if there's something that's aqueous, as you saw up here, the first thing you have to do is write a list of all the reactants and products as you find them in the actual beaker, not like stuck together, because they're not stuck together. So what next? So the next thing we have to do is write the equation with the spectator ions not involved. So what's really happening here is the copper metal is reacting with the silver ions, producing copper 2 ions and silver metal. Okay, so in my class we have to determine what's really going on in this particular case. Now we have 3 choices that we've talked about. We've talked about redox reactions where there's electrons transferred. We've talked about precipitate reaction where there's some ions that stick together. And we've talked about acid-base reactions. Okay, so we have to determine which reaction type this is because it changes how we proceed. Well, if copper has no charge and now copper has a charge, well, the way things get a charge in chemistry is by passing electrons. That means this is a redox reaction. Okay, so once we've identified it's a redox reaction, we have to make sure that the electrons gained equal the electrons lost. So from copper's point of view, we kind of drew an arrow like that when we first learned it and said, well, that process, let's see, that would be losing 2 electrons because you went from a 0 charge to an excess positive charge, which means you lost negatives. And the silver ions must have gained 1 electron to get from a +1 to a 0. Now you cannot have the electrons gained not equal the electrons lost. And so we learned how to balance the net ionic equation by looking at the electron change. In fact, we learned later when we balance complicated redox reactions to sort of write the 2 half reactions. So from copper's point of view, it started off with all of its electrons and it ended up with 2 electrons that were no longer connected. The silver ions picked up an electron and became silver metal, and we learned that this one will have to happen twice so that there's 2 electrons gained and 2 electrons lost. now we have a balanced net ionic equation because we can write copper and 2 silver ions create copper 2 ions and 2 silver atoms. Okay, this is what we need to do stoichiometry in my class. In my class, stoichiometry is always start with the net ionic equation and determine the starting amount of moles for each, see which pile runs out, and then use the limiting reactant pile to determine how much product. So how do you do that? Well, let me give myself a little room up here. We now have the net ionic equation, okay, which was 2 silver ions and 1 copper make 1 copper 2 ion and 2 silvers. Okay, so there's our net ionic equation. So we need to take these starting values and determine the starting values of each of the reactants in the net ionic equation. So let's do that. Let's begin with the silver. The silver, we said, was 300 milliliters at 0.5 moles per liter. So let's do a little math here. 1,000 milliliters is a liter, and we've said each liter right here is 0.500 moles of AgNO3. Now, it's not the silver nitrate that I want to talk about. I want to talk about silver ions. So to determine the amount of silver ions, I'll do one final step that says if you take a mole of silver nitrate and break it into pieces, you'll get 1 mole of silver ions. Now, you'd get 1 mole of nitrate also. We're just not using the nitrates because they're spectators. When you do this math, that comes out 0.15, let's see, sig figs, 3 sig figs, moles of silver ions. Okay? That's the number that goes right here. Okay? And we'll say 0.150 moles is my starting amount of silver ions. Now let's find the starting amount of copper. Well, that's a solid. Okay, it's not aqueous. So I'll use the atomic mass and say 5 grams of copper. Let's see, from the periodic table, there are 63.546 grams of copper per mole of copper. And if I do that math, let's see, 5 divided by 63.546, you get 0.078, let's see, 3 sig figs, that'd be 7 moles of copper when you start. That's the number that goes right here, 0.0787 moles. Okay, now, because I have a balanced net ionic equation and I have the starting amounts, this product should look like what we did in the stoichiometry video. And that's the goal of all of these reaction types, is to first change them so that they look just like we're used to, the balanced equation that we'll do stoichiometry from, and the starting amounts. Now, the original equation I had up here, you could balance this and do things from it. But for us, we want to focus on what's really happening in the containers, and so we'll look at this. Now, which pile runs out first? Let's see, I need twice as much of that. So let's just see. Let's do a quick calculation to determine that. If I have 0.150 moles of silver ions, and it takes 2 moles of silver ions for every 1 mole of copper, that should come out 0.0750 moles of copper needed. I have 0.075. Oh, it looks like I have enough copper, and the silver ions will be the limiting reactant, and that's what I would use to determine the amount of product. Okay, so there's an example with a redox reaction. So what did we do? We first took our entire equation and wrote it as ions. Then we got the net ionic equation. Since it was redox, we had to balance the electrons. And then we figured out our starting amounts and did stoichiometry. We've also done things in class where there's other types of redox reactions that are more complicated, but I'll tell you, or you'll be able to tell right away if it's a redox reaction of this form, because we gave problems like this where I just said there's the starting reactants, there's the products, and we did it in acid. And as soon as I say that, you have to know that's a redox reaction. And so we learned how to balance those. When we got done, we ended up with 8 H pluses, 2 NO3 minuses, 3 coppers, let's see, 2 nitrogen monoxides, 3 copper 2 ions, and 4 waters. And we had a large series of steps that gave us that equation. Now, what good is that equation? Well, that is the net ionic equation. So if I had starting amounts of the nitrate ion and the copper metal, they would go there. I would determine which pile runs out and continue from that point. Okay.